Imagine looking back in time, almost to the very beginning of the universe. That's what JWST is doing, peering into an era just a few 100 million years after the Big Bang. What it's finding there is nothing short of astonishing and deeply unsettling for our current models. Our standard cosmological model, Lambda CDM, predicts a gradual hierarchical formation of galaxies. Small clumps of matter should slowly merge and grow over billions of years, eventually forming the massive complex structures we see today. The early universe, according to this model, should be populated by small, nascent galaxies, still in their infancy. JWST, however, is revealing something entirely different. It's spotting galaxies in the cosmic dawn that are surprisingly massive, incredibly bright, and remarkably mature. Some even exhibit complex structures like disks and barred spirals, features that should take far longer to develop. These early giants appear to have formed and evolved at an impossibly rapid pace, defying our expectations. This discovery directly challenges the Lambda CDM model's timeline for galaxy formation. It suggests that the universe was far more efficient at building large structures in its infancy than we ever imagined. How could such massive galaxies assemble so quickly when there simply wasn't enough time for the slow gravitational accretion process we currently understand? The existence of these mature early galaxies forces us to reconsider fundamental aspects of cosmic evolution. Did supermassive black holes form much earlier, perhaps acting as seeds for rapid galaxy growth? Were the conditions for star formation drastically different in the early universe, leading to bursts of intense stellar production? Or are there limitations in our current models of how dark matter and baryonic matter interact to form these colossal structures? These questions are not minor tweaks. They point to potential gaps in our understanding of the universe's earliest moments. The very processes that govern the birth and growth of galaxies might need a radical re-evaluation. It's like finding fully grown trees in a forest that was planted only yesterday. Beyond individual galaxies, JWST is also exacerbating one of cosmology's most persistent and frustrating puzzles, the Hubble tension. This isn't just a minor disagreement, it's a fundamental discrepancy in how we measure the expansion rate of the universe. The Hubble constant, denoted as HO, is a crucial parameter that tells us how fast the universe is expanding at any given time. There are two primary ways to measure HO, and they yield significantly different results. One method relies on observations of the early universe, specifically the cosmic microwave background CMB radiation. This ancient light, a relic from just 380,000 years after the Big Bang, provides a snapshot of the universe's initial conditions. By extrapolating forward using the Lambda CDM model, scientists derive a value for HO. The second method involves measuring the expansion rate in the local universe using a cosmic distance ladder. This involves observing standard candles like Cepheid variable stars and Type Ia supernovae, whose intrinsic brightness is known. By comparing their apparent brightness to their known luminosity, astronomers can calculate their distance and thus the expansion rate of the space between us and them. The problem is these two methods produce values for HO that are statistically incompatible. The CMB-derived value is consistently lower than the local universe measurements. This Hubble tension has been a growing concern for years, but JWST's precision has made it even more acute. By providing incredibly sharp and accurate measurements of distant stars and galaxies, JWST has effectively ruled out measurement errors as the primary cause of this discrepancy. The confirmation of the Hubble tension by JWST data suggests something profound is amiss. It implies that either our understanding of the early universe is flawed, or there's new, unknown physics at play in the cosmos. This isn't just a scientific puzzle, it's a crisis, as Nobel laureate David Gross has described it. It suggests that our standard model of cosmology, which has been incredibly successful for decades, might be incomplete or even fundamentally incorrect. What could be causing this tension? Scientists are exploring a range of exotic possibilities. Could there be a new, unknown particle influencing the universe's expansion? Perhaps a form of weird dark matter or evolving dark energy that behaves differently than we currently understand. Some theories even propose a magnetic field in the early universe or a new fundamental field that alters the expansion rate. The Hubble tension is a direct challenge to our most cherished cosmological assumptions, pushing us to the very edge of known physics. Early in JWST's mission, some initial observations sparked headlines about universe-breaker galaxies. These were thought to be incredibly massive, incredibly early galaxies that seemed to defy all cosmological expectations. The excitement was palpable, with some scientists suggesting that a radical change in cosmology was immediately needed. However, as more data poured in and analysis became more refined, the picture became clearer. It turned out that the distances to some of these initially identified galaxies were overestimated. This led to an overestimation of their stellar masses. When the distances were corrected, their masses, while still significant for their age, were not quite as universe-breaking as initially thought. While these galaxies may not break the universe in the most dramatic sense, they still present a profound challenge to current models. Even with refined measurements, these early galaxies remain remarkably massive and mature for their age. They still require incredibly rapid formation processes that are difficult to explain within the standard Lambda CDM framework. The story of the universe-breaker galaxies highlights the dynamic nature of scientific discovery. Initial observations can be startling, but further data and rigorous analysis are crucial for refining our understanding. It also underscores the power of JWST to push the boundaries of what we thought was possible, even if the initial interpretations are later adjusted. These galaxies, while not quite the cosmic behemoths first imagined, still demand new explanations for how structure formed so quickly in the early universe. When the standard model faces such significant challenges, scientists naturally turn to alternative theories. While these models are often considered outside the mainstream, the persistent anomalies from JWST are prompting a renewed interest in them. They offer different frameworks for understanding the universe, potentially providing solutions where Lambda CDM struggles. One intriguing alternative is conformal cyclic cosmology, CCC, proposed by Nobel laureate Roger Penrose. This theory suggests that our universe is not a one-off event, but rather one in an infinite chain of eons. Each eon begins with a Big Bang and ends with an infinitely expanding empty universe, which then becomes the Big Bang of the next eon. In this model, the very distant future of one eon is conformally equivalent to the Big Bang of the next. Penrose suggests that remnants from previous eons, such as supermassive black holes, might leave detectable traces in our current universe. Some scientists have speculated that the early massive galaxies discovered by JWST might align with predictions from CCC, perhaps hinting at structures inherited from a previous cosmic cycle. It's a radical idea, but one that offers a way to explain phenomena that seem to defy our current understanding of cosmic origins. Another historical alternative is the tired light theory. This theory, first proposed in the early 20th century, suggests that the redshift of light from distant galaxies is not due to the expansion of the universe, but rather to the light losing energy as it travels through vast cosmic distances. Imagine light waves getting tired and stretching out as they journey across billions of light years. While largely discredited by observations like the cosmic microwave background and the time dilation of supernova, hybrid models that combine tired light with an expanding universe are still being explored by a minority of researchers. Even more radical is the idea of a static universe. This theory posits that the universe is not expanding at all. If the universe isn't expanding, then the observed redshift of distant galaxies must be explained by other factors. Some proponents suggest that fundamental constants like the mass of particles might change over time, leading to a redshift effect. While the evidence for an expanding universe is overwhelming for most cosmologists, the persistent anomalies from JWST, particularly the Hubble tension, encourage a small number of scientists to revisit even these long-discarded ideas. These alternative models, while not widely accepted, represent the scientific community's willingness to explore new paradigms when faced with challenging data. They remind us that our current understanding, while robust, is always subject to revision in the face of new, compelling evidence. JWST is providing that evidence, forcing us to consider possibilities once thought to be firmly in the realm of science fiction. The profound implications of JWST's findings are not lost on the scientific community, especially those at the forefront of cosmological discovery. Nobel laureates, who have shaped our understanding of the universe, are openly acknowledging the challenges posed by this new data. Their statements underscore the seriousness of the situation and the potential for a paradigm shift. Adam Rees, who shared the Nobel Prize for the discovery of dark energy and the accelerating expansion of the universe, has been particularly vocal. He has stated that the JWST findings suggest we have misunderstood the universe. This is a powerful admission from a scientist whose work is foundational to our current cosmological model. Rees also acknowledges that the Hubble tension, a problem he has been deeply involved with, has only worsened with JWST's incredibly precise data. His words highlight the growing unease within the scientific community about the fundamental assumptions underlying our cosmic theories. Similarly, David Gross, a Nobel Prize-winning theoretical physicist, has referred to the Hubble tension as a crisis. This term is not used lightly in science. It signifies a situation where existing theories are unable to explain observed phenomena, demanding new theoretical frameworks or a re-evaluation of fundamental principles. When leading minds in physics and astronomy use such strong language, it signals that the challenges posed by JWST are not minor anomalies, but potentially indicators of deeper, unresolved issues in our understanding of reality. These statements from Nobel laureates are not expressions of defeat, but rather a call to action. They signify that the scientific process is working as it should. New, precise observations are challenging existing models, forcing scientists to question, innovate, and explore new frontiers. The universe, it seems, is far more complex and mysterious than we ever imagined, and JWST is pulling back the curtain on its deepest secrets. In summary, the James Webb Space Telescope is not just giving us stunning images. It's providing an unprecedented view of the early universe that is challenging some of our most fundamental assumptions about cosmology. While some initial universe breaker concerns have been refined with further data, significant puzzles remain. The existence of surprisingly massive and mature galaxies in the cosmic dawn defies our current understanding of galaxy formation. Even more critically, JWST's precision has deepened the Hubble tension, confirming a fundamental discrepancy in the universe's expansion rate. These challenges are not just academic curiosities, they are prompting scientists to explore new ideas and alternative cosmological models, pushing the boundaries of our knowledge. The universe is revealing itself to be more complex and enigmatic than we ever imagined. We are at a pivotal moment in cosmology where new discoveries are forcing us to reconsider the very fabric of reality. What do you think these cosmic mysteries mean for our understanding of the universe? Are we on the verge of a new revolution in physics? Share your thoughts in the comments below. If you found this journey into the cosmic unknown intriguing, hit that like button, subscribe for more deep dives into science, and ring the notification bell so you don't miss our next exploration of the universe's biggest questions. Let's continue to unravel the cosmos together.